In example 5, consider the definite integral from 0 to 4 of x plus 2 with respect to x, which represents, of course, the area between this function, x plus 2, the x-axis in between x equals 2 and x equals 4. And notice that it traces out a trapezoid there. So the actual question is it possible to construct a rectangle that has the same base length, and so the base length here looks like it's a 2, and the same area as this definite integral? Well, in order to be able to tell, let's actually find the value of the definite integral. Should be pretty easy because we don't have to actually find the definite integral's antiderivative. We could just find the area of that trapezoid. So the area of this trapezoid, we need the two base lengths. The two base lengths are actually the function values here. On the left-hand side, we got 4. On the right-hand side, we've got 6. So we add those two together. 4 and 6 gives us 10. Multiply it times our height of 2. That gives us 20, but then we need to take half of it. So the value of that definite integral is 10. Area of that trapezoid is 10. Is it possible to make a rectangle that has an area of 10 and has a base length of 2? Well, of course we can. It would just be 5 times 2, right? 5 would be the height of that rectangle. Not only is 5 the height of that rectangle, but notice that that 5 is actually a function value. That 5 is the average value of that function. And the rectangle that we got there has the exact same area as the area underneath the curve. It's the same thing that we've been seeing playing out throughout this whole entire lesson. So this is going to lead us to what we call the mean value theorem for rectangles. Not only can you find that rectangle that has the exact same area underneath the curve, but the height of that rectangle is a function value over that closed interval. All right, let me take you back through some of those pictures here. So let me come back over here. All of those pictures that had rectangles in it, like, for example, this one. The area of this rectangle, which we're calling the mean value rectangle, has the exact same area as the blue region here. We can see that there's this little extra blue bit that should fit nicely in these two spots that are right there. Now, rectangles are supposed to be what we're using to approximate the area. And we're saying that it's exactly equal to the value of the area underneath the curve. It's very similar to the MVT for derivatives. We're using the slope of a secant line, which we're using usually to approximate a tangent line, and we're saying that that is exactly equal to the tangent line some point on that interval. That was the MVT as we're used to seeing it. Okay, so of course this froze on me. Let me come back in here and go back in here. Are you going to unfreeze? Okay, so no, we're not going to unfreeze. Instead, we're just going to come back over here, and let's take a look then at the Goldilocks rectangle. So it's officially called the mean value rectangle. I like to call it the Goldilocks rectangle for this reason. So if you're unfamiliar with the story of Goldilocks, again, it's the one where there's this little girl goes into this bear's house, not a cave, of course, a bear's house, and eats some porridge. One's too hot, one's too cold, one's just right. It's just like that. So if you look at the picture that's over here on the left-hand side, if I find the minimum value of the function, I can use that height to inscribe a rectangle within our shape, and of course its area would be way too small. If over there on the far right-hand side, we find the absolute maximum value of our function, we can use that as the height of a rectangle, which should circumscribe, completely go around our function and the area underneath it. Its area would be too big. The mean value rectangle, on the other hand, it's the Goldilocks one. It's the one whose area is just right. It uses the average value as the height over the span between A and B to give you the exact area underneath the curve. All right, so let's write something down then for the mean value theorem for integrals. This will eventually make its way onto our memory card. So if f is continuous, it's a continuous function on the closed interval from a to b. So there's the condition that has to be met before you can apply this. Then there exists a number c in the closed interval such that whoop, the definite integral from a to b of f of x dx is equal to f of c times b minus a. F of c is the height of that rectangle. B minus a is that base length that's right down there. Okay, what is f of c? F of c, of course, is the average value of our function. The average value of our function, as I'll show you, that's right here. So if I take this and I just solve it for f of c, I'm going to get this b minus a, bring it over to the left-hand side, and you can see that 1 over b minus a times the definite integral from a to b of f of x dx is equal to the height, and that's exactly how we defined the average value earlier in this lesson. All right, so all we're going to do here is one extra little problem just to practice this. Right here on example 6. This is assuming that I'm going to be able to get Notability to work for us if it's not frozen. I don't know, we'll see. Find the value of c guaranteed by the mean value theorem for integrals for f of x is equal to 1 plus x squared over this closed interval from -1 to 2. So let's see here. It is indeed definitely, oh, well, there we go. I was able to actually use the little finger tool. Okay. All right, hey, ignore the picture there. And let's see, this was example, I think 6. And our function f of x is equal to 1 plus x squared. We're going over the closed interval from -1 to 2. Okay, now, if this was a free response type question, we want to make sure that we point out that our function satisfies the conditions of the particular function. And we said, in order for us to be able to apply the mean value theorem for integrals, our function needs to be continuous. Is our function continuous? It is indeed. And the reason why it is because it's polynomial. So I'm going to point this out. Since f of x is polynomial, it is continuous everywhere. So MVT for integrals applies. So now we've met our conditions, and now let's just go ahead and apply it. And notice that the question is asking for what is this value of c? In order to see what that is, all we're going to do is set this up exactly like we did in the definition here, or actually in the theorem. We're going to find the definite integral. We're going to set it equal to some sort of function value times the b minus a, which is the width of that interval. Okay, so we have the definite integral from -1? Yeah. -1 to 2 of our function 1 plus x squared dx. -1 to 2. What is this down here? I don't even know. -1 to 2 should be equal to some sort of function value, I'll make it a c, times b minus a. And our b minus a is 2 minus a -1, so plus 1, gives me 3. So I've got definite integral from -1 to 2, 1 plus x squared dx is equal to 3 times f of x. Well, f of c, I should say. If I were to divide this 3 over, remember what that would just be giving me is the average value. And this average value is going to be the height of our rectangle. Mean value, a rectangle. So let's just go ahead and solve this left-hand side over here, finding its antiderivative. Antiderivative of 1 is just x, plus we'd have an x cubed over 3. We're going to evaluate that from -1 to 2. And again, this is still equal to 3 times f of something. Okay, and now we're going to plug in our values. And let's see what we get. We get 2 plus 2 cubed over 3 minus a -1. And whenever I cube -1, it's going to preserve its negativity. So it'll be -1 over 3. All this still equal to 3 times f of c. And now let's do some arithmetic and simplify this. Is this a safe stop? It absolutely is not. 2 plus 8/3, I want to say, And then let's distribute our negative sign through here. So minus and minus makes it a +1 plus 1/3. Okay, we've got a total of 3 there. And then we'd have 8/3 plus 1 more third gives us 9/3, which is another 3. 6 is equal to 3 times f of c, which means that f of c is equal to 2. Zoop, zoop, zoop. Okay. Is that the answer to the question? It says, no, it says find the value of c. That's guaranteed. So what we just found was the average value. So that's another way to actually work this problem, is that, like, instead of having this 3 over here on the right-hand side, whenever we set this up, we could have just written 1/3 and found the average value. And then whenever we got the average value, we'd be right here at the same exact position. Now we want to know, where does our function hit to? In order to find that out, we just set that equal to our function. And our function was, the original function is 1 plus x squared should be equal to 2 someplace. I'm going to subtract the 1 over. X squared is equal to 1, so x is equal to either plus or minus 1. So we got 2 different values here. Whoops. Hey, pink. Are they in our interval? Only one of them needs to be, and we're going from -1 to 2. On -1 to 2, it actually both of them hit it on there. And now notice this is strange for this particular theorem, is that if I come back over here to the actual statement of the theorem, that c value is in a closed interval. It's not in an open interval, which means that the c value can be one of the endpoints, which it definitely happened right here. It was this endpoint, and then it hit someplace further down the line over here at 1. Hit at both positive and -1. All right, so that concludes this lesson here on the mean value theorem, or the average value of a function over some sort of closed interval. And in order to find it, we're taking some sort of fraction that goes right up front, which is 1 over b minus a times the definite integral from a to b of our function with respect to x. Okay, that concludes the lesson. Don't forget your homework supplement.